This video is one of a series of videos I've made for students who are learning physics to prepare to enter a diagnostic medical sonography program. To find other related videos, please see my playlist, Physics for Diagnostic Medical Sonography Students. In this video, we're going to cover thermal energy, temperature, and thermal expansion. In our previous video, we reviewed the ideas that all matter is made up of atoms and molecules. Remember that molecules are made up of atoms. So for example, a water molecule is H2O, made up of 2 hydrogen and 1 oxygen atom. Remember too that an atom is the smallest amount of an element that we can have, and a molecule is the smallest amount of a compound that we can have. In this video, we want to talk about the internal energy of an object, and that's what we call thermal energy. So think about thermal energy as it's the internal energy that an object has. And the first thing we want to understand is, well, what does that really mean? Well, when an object becomes warm, it has more thermal energy. And what's happening there is the atoms and molecules that make up the object start to move more. So the individual atoms or molecules have more energy. Now this is easier to understand with liquids and gases because we know those atoms or molecules can move around freely. But in a solid, we think of the atoms or molecules being kind of locked in place. But in reality, they're not. They can move back and forth relative to each other. And so often we model this by showing our atoms here connected by springs. So you can imagine that those, even though the atoms or molecules are stuck in that structure, they can vibrate back and forth. And when the object gets warmer, those atoms or molecules are going to vibrate more. Just like in a liquid or a gas, they're going to move around more. And in a liquid and gas, they can not only move, but they can turn as well. So they can be rotating or translating, moving, as well as just kind of vibrating like they do in a solid. So that's what thermal energy refers to. Thermal energy is the total potential and kinetic energy of all the atoms and molecules in a substance as they move about, rotate, and vibrate, etc. So we talked about potential and kinetic energy in an earlier video. Remember that kinetic energy is the energy of motion. So simply the more the objects are, the more the atoms and molecules are moving, the more kinetic energy they have. Atoms and molecules only want to get so close to each other or so far apart from each other, and that's the part that is potential energy. So just like when we take a mass and we pull it away from the Earth, it wants to fall back towards the Earth. We know that as we raise up that object, it has potential energy. Here, it's electrical potential energy, which we'll talk about later in the course. But anyway, thermal energy is the total amount of energy that all the atoms and molecules have in the object. Now let's talk about temperature. Temperature is a related but different concept. Temperature is proportional to the average kinetic energy of the atoms and molecules that make up the substance. And therefore, the greater the temperature, then the greater the average kinetic energy is of those atoms and molecules in the object. So in a very hot object, when we measure the temperature, we get a high temperature, and it's because those atoms and molecules have more movement. They have more energy. Let's look at a couple examples to help us understand the difference between total energy, meaning thermal energy, and average energy, meaning temperature. So let's look at this question. You're baking an apple pie for your physics professor. You'll notice that's a hint. It's always a good idea to bake an apple pie for your physics professor. The oven is set to 350 degrees. If you put your hand in the oven but don't touch anything, do you get burned? Now I'm sure you've all experienced a hot oven and know that no, you don't get burned. So why not? Because the temperature of that oven is 350 degrees. But even though that means that the average molecules have a lot of energy, remember that it's just air in the oven, and there are not that many molecules. In other words, the density of the air is low. And so there are not that many molecules that can bump into your hand and transfer energy to you. So the average temperature is high, but the thermal energy in the air in that oven is low. Now, what if you take your finger and you stick it into that hot apple pie just as it's come out of the oven? Well, notice that the temperature of that filling is also going to be 350 degrees, the same temperature as the air was in the oven. But now you are going to get burned. Well, why is that? We know that that filling contains a lot of thermal energy. It's dense. There are a lot of molecules in there that are vibrating. So when you stick your finger into that dense material, a lot of thermal energy can be transferred to your finger and you get burned. So the temperature is the same. So same temp, but very different thermal energy. Okay, so let's look at another example. Which has a higher temperature, a small red hot coal or a tub of warm bath water? Well, that's pretty obvious. Let's say that our little red hot coal over here is maybe 150 degrees Fahrenheit. And our tub here we've got filled with water, and it's a nice warm bath, so let's say the temperature is 80 degrees Fahrenheit. Well, clearly the coal is going to be hotter. It's got a higher temperature. But which has more thermal energy? Well, the coal is small, so even though all the molecules, or the average kinetic energy of those molecules in that coal is high, there are not that many of them. Whereas here, we've got a lot of water molecules that are moving, and even though an individual molecule isn't moving as fast as it is inside the coal, there's so many more of them that clearly the tub is containing more thermal energy. Why don't you pause the video and try this one on your own? A small iron nail, mass 10 grams, is heated to 100 degrees Celsius. A large iron block, mass 1 kilogram, is heated to 50 degrees Celsius. Which statement is correct? So before I even read the answers here, one of the things that I know is that the temperature of the nail is definitely greater than the temperature of the block, because the nail is at 100 degrees and the block is at 50 degrees. But I can also see that the mass of the block is greater than the mass of the nail. And it's significantly greater, right? 1 kilogram, remember, is 1,000 grams. So that's 100 times as much mass as the nail. And so you can probably see where this one's going. Let's look through the answers. The nail has a higher temperature, so it has more thermal energy. Well, the nail does have a higher temperature, but it definitely doesn't have more thermal energy. The block has a lower temperature, so it has less thermal energy. Nope. The nail has a higher average kinetic energy per particle, so that's true, because remember, average kinetic energy is temperature, so that's true. But the block contains more total thermal energy because of its larger mass. That's also true. And so we can see that C is the correct answer. We'll notice D doesn't make sense. It says they have the same thermal energy, but they clearly don't. Here's a question. When an object slows down to friction, where does all the kinetic energy go? So one of the things that I want you to just pay attention to is that when we've been talking about kinetic energy over the last number of slides, we've been talking about the kinetic energy of the molecules and atoms inside an object. But now we're talking about kinetic energy like we did when we were talking about energy in motion. So here I've got an object, and let's say that it has some initial velocity v0 of 2 meters per second. And we know that if we start that block with that initial velocity, and it's just a block on the table, we know what's going to happen is that block is going to come to rest. And so clearly it had kinetic energy initially, but the kinetic energy at the end is zero. Where did that energy go? Well, we know from conservation of energy it had to go somewhere. Well, where it goes is into the internal energy of the two objects. So, in other words, that internal energy, which is what we call thermal energy, is where that initial kinetic energy ends up. So that friction causes the molecules within both the surface of the table and of the block itself to have more motion than they did before. One of the things, just to try to illustrate this, is if you take your two hands and put them together, and now rub them back and forth. And you'll notice if you push your hands hard together and rub them back and forth, your hands get warm. And that's because you're converting that kinetic energy of moving your hands into thermal energy inside your hands. And that's why your hands warm up. So that's what happens when we have friction involved, that we lose the kinetic energy of an object and it goes into the internal or thermal energy of the objects that are in contact. So the molecules within those two objects now are moving more than they were before. Let's talk about temperature. Earlier in the course we did some temperature conversions, but let's talk a little bit more about the different temperature scales that we want to be familiar with. In the United States, we still tend to use the Fahrenheit scale in our everyday lives. In most other places in the world, we use the Celsius scale. And then in science and medicine, we use the Celsius scale as well. So there's nothing really good or bad about these different scales. They're just different. You'll notice, though, that they're set by where water boils and where it freezes. So on the Fahrenheit scale, 32 degrees is freezing and 212 degrees is water boiling. On the Celsius scale, it makes more sense. We say 0 Celsius is water freezing and 100 degrees is water boiling. One of the things to notice about these two scales is that the difference in temperature between freezing and boiling for Fahrenheit is 180 degrees Fahrenheit, whereas the difference between freezing and boiling on the Celsius scale is 100 degrees Celsius. What that shows you is that a Fahrenheit degree and a Celsius degree are different. And that's why when we have to do the conversion, there's that fraction that's involved, because you'll notice that Fahrenheit degrees are smaller because there are 180 of them between freezing and boiling, whereas there are only 100 Celsius degrees between freezing and boiling. If we look at the Kelvin scale, you'll notice that a Kelvin degree has the same size as a Celsius degree because the difference between freezing and boiling water is 100 degrees Kelvin. So it's the same as for Celsius. And that's why the conversion between Celsius and Kelvin is so simple. The only thing that's really different is where we set the 0. So let's look at why do we set Kelvin so that freezing water is at 273 degrees. Well, the reason is that the Kelvin scale is related to what we call absolute zero. Absolute zero is the lowest temperature possible. We've said that temperature is a measure of the average kinetic energy of the atoms and molecules that make up the substance. So you can imagine the lower the temperature, the less energy, kinetic energy, the atoms and molecules have. And so you can imagine that there is a point where you remove all of the energy. And so that would be the lowest possible temperature, and that's what we call absolute zero. And that's how we set the Kelvin scale. So 0 degrees Kelvin is absolute zero. There is no practical upper limit limit to temperature. So you can imagine that really the higher the temperature, the higher the kinetic energy of the atoms and molecules. So for example, in a gas that's raised to a very, very high temperature, there's essentially no upper limit to that. Here are the conversions between Celsius and Fahrenheit and between Kelvin and Celsius that we covered earlier in the course, but we'll just review them here. Again, now we understand why we have these fractions here when we're going between Fahrenheit and Celsius. It's simply because 1 degree Fahrenheit is not the same size as 1 degree Celsius. However, because a Celsius degree and a Kelvin degree are the same size, that's why we get the simple conversion here. You'll notice the only thing we're doing is taking care of the fact that the zeros are in different places. So let's just do one practice problem to remind us how to use these formulas. An object has a temperature of 92 degrees Fahrenheit. What is the temperature in Celsius and what is it in Kelvin? Why don't you pause the video and just go ahead and convert those for me. Okay, well, let's go over these and make sure that you got them right. The first thing we have to understand is that we're starting with Fahrenheit and we want to end up with Celsius. And so if we go back here, we see that this is the formula we want because we know what to plug in for F, and what we're trying to get is C. And so the first thing I'm going to do is just write down that formula. C is equal to 5/9 times F minus 32. And now we're already solved for what we're looking for, which is Celsius. And so we can just plug in the values. C is equal to 5/9 times 92 minus 32. And that gives me 5/9 times 60 degrees. And now we just have to multiply by 5 and divide by 9. And keeping 3 digits here, I got an answer of 33.3 degrees. And that would be degrees Celsius. Let's see what we get when we convert to Kelvin. So Kelvin is the easy one. Kelvin is just C plus 273 degrees. And so in this case, we get 33.3 plus 273, or 306.3 degrees. And we'll put degrees K for just to represent what it is we're talking about. So if it's unambiguous which scale you're using, you can just use degree. But if you're doing a problem where you're differentiating between them, then it's good to do degrees Fahrenheit or degrees Celsius or degrees Kelvin as your unit, just to emphasize which it is that you're using. The last thing we want to look at in this video is thermal expansion. Most materials expand when their temperature increases and contract when it decreases. And this is something you're probably familiar with. Here's a good example, and that is, let's say you have a jar that has a lid that's hard to remove. So one of the things that you may have tried before is you can put the lid under hot water. So you start the hot water going in your sink and you hold the lid under the faucet, and you do that for a little bit till the lid gets hot, and then if you try opening it, it's usually pretty easy to open. Well, what we're using there is this idea that materials expand when their temperature increases. And if we can get that lid to increase in size, it's going to more easily come off the jar. Now, obviously, ideally, when you're doing that, you don't want the hot water getting too much on the jar because we don't want the jar expanding as well. However, it turns out that different materials expand at different rates, and that metal is actually going to expand more than the glass is anyway. So, what's the formula that describes this? Here's the formula that relates the amount that the object expands, so that's delta L, Notice we're just using delta to mean change as always. So the length will change by an amount delta L. And that's equal to alpha. We use the Greek letter alpha to represent something called the coefficient of linear expansion. And that's different for different materials. So different for each material. And that's something you can look up or you'd be given on a homework or an exam. L is the length, the current length of the object before the temperature change, and delta T is the change in temperature. One of the things we want to look at here is we have to be a little bit careful with units. Let's look at what the units are. So we know that delta L, the change in length, generally is going to be in meters. And that means that L also is in meters. Temperature, generally we're going to measure in degrees Celsius, so degrees C. And so the question is, what units does alpha have? Well, remember that for an equation to be valid, the units have to be the same on both sides of an equation. And let me just write that because that's an important concept. So units have to be the same on both sides of an equation. So that's an important thing to remember. And so you'll notice the only way we can make this work is if alpha has units of 1 over degrees Celsius. And so when you see a value for alpha, you'll notice it will have 1 over degrees Celsius as its unit, because that way those would cancel out and we'd end up with meters on both sides. The other thing is the length could be in centimeters instead of meters. That would be okay as long as delta L and L must have the same units. So must be in the same units. And so that could be centimeters or meters, but just make sure that both L and delta L are in the same units. All right, let's try this out. So it turns out that this idea that materials expand or contract is actually how we make thermometers. So why does a mercury thermometer work? Well, because it works with the underlying principle that if you heat up any material, it will expand or contract. And so in an old-fashioned mercury thermometer, you got a bunch of mercury in the bottom, and as you put the bottom of the thermometer in something that's warm, the mercury expands up a narrow tube there. So the length of that column expands. And if we know how mercury does that, then we can mark our thermometer appropriately. So let's do an example with that. What is the change in length of a column of mercury in a thermometer when the temperature changes by 5 degrees? The current length of the column is 8 centimeters, and the coefficient of linear expansion for mercury is 6.1 times 10 to the negative fifth per degree Celsius. So again, that's how you'll see that unit written as 1 over or per degree Celsius. Let's just identify what we have here. You'll notice first of all that we've been given the length of the column, that's L, and we've been given it in centimeters. It's okay to leave it in centimeters, just know that delta L then will have units of centimeters. Alpha, we can see, has been given as 6.1 times 10 to the negative 5 per degrees Celsius. And delta T is 5 degrees, and we can assume that that's 5 degrees Celsius. And so now we just need to plug into the formula. We have delta L is equal to the coefficient of linear expansion times the length times delta T. So we get 6.1 times 10 to the negative fifth times 8 times 5. And if you work that out, you should get 0.00244. And again, the length will be the same as the length for L, so that would be centimeters. Probably a good idea to rewrite that in scientific notation. So let's see, 1, 2, 3. So that would be 2.44 times 10 to the negative 3 centimeters. All right, let's do one last example. Might be a good idea to pause the video here and try this one on your own. So this problem says a copper rod has an initial length of 2 meters. After heating, its length is increased by 0.102 centimeters. And there's a little warning there to be careful. The coefficient of linear expansion for copper is 1.7 times 10 to the negative fifth. What was the change in temperature? So let's use our good problem solving methods here and identify everything we know and what we don't know. We can see that we're given the initial length. So L is 2.00 meters. We've also been given delta L. So we're told the length increases by 0.102. So delta L is 0.102. But notice that we were given that in centimeters. And we know that L and delta L have to have the same units. Right? So these have to have the same units. And I could convert either way, but I'm going to convert centimeters to meters. So I know that in 1 meter, there are 100 centimeters. And the other way you could do that is just remember that centa is 10 to the minus 2. Anyway, in this case then, I'm going to get 0.00102 meters. And if you want to put the 0 in front of the decimal, you can. So I'll write it as 0.00102 meters. Okay, once we've got delta L, now let's see what else we have. We can see that what we're looking for is delta T, and we've been given alpha. So now we've identified what we know and what we don't know. Starting from our equation, delta L is equal to alpha L delta T. You'll notice the first thing we want to do is solve that for delta T. So I'm going to divide both sides by alpha L. So those will cancel out. And what I'm left with is that delta T is equal to delta L over alpha L. Now I'm ready to just plug in the values. So delta L was 0.00102. We could have rewritten that in scientific notation if we had wanted to. And then we're going to divide by alpha, which is 1.7 times 10 to the negative fifth, and L, which is 2. So when you do that calculation, you should find that delta T is 30 degrees Celsius. So that would be the change to get that change in length. One other thing to say about this formula is that, of course, it can work the other way. If you're told that the temperature goes down by an amount delta T, then that will be the amount that the object shrinks. So this works both for expansion and shrinking due to temperature change. In our next video, we're going to be talking about the concept of heat and how it relates to thermal energy that we've talked about in this video.